Action! Right now, our world is at a tipping point with climate change,
Climate change is real.
Climate change.
Climate change.
Climate change.
overpopulation,
The world's population has doubled in less than 50 years.
Global overpopulation.
dwindling mineral resources,
Limited availability of the crucial metal.
and famine.
We've found ourselves living in a global food crisis.
5.5 million people are facing hunger.
Effects of extreme hunger obvious in
Food crisis.
These are crises that threaten our very existence. But there's hope beyond Earth, not just for survival, but to expand, innovate, and inspire. Mars, a planet that has the potential for human presence, long-term habitations, and the resources to fuel scientific, economic, and cultural growth. Yet, the way we approach space exploration is not enough. It's a little bit outdated, it's inefficient, and limited in scope. But here's the exciting part. New technologies are being developed that can make our dream or fantasy of interplanetary life reality. In this video, I will take you with me and explain to you why do we even bother to go to space? How do we even get there? And what are some challenges we face and some innovative solutions? With all the challenges Earth is facing right now, you might wonder, why do we even spend energy and resources for space exploration instead of focusing on solving problems here at home? Isn't just an expensive fantasy? Actually, space exploration might be the key to solve some Earth's biggest problems and unlock humanity's greatest potential. Protecting Earth, fueling growth, satisfying our urge to explore, these are the reasons why we venture into space. And it's not easy to achieve all that. Question is, how are we even gonna get there? This is how electrical propulsion comes in, revolutionizing the way we navigate the cosmos. Chemical propulsion systems, the kind we use for liftoff, are like sprinters. Immense power, but only for short bursts. Now, compared to electrical propulsion's one, think of it as a marathon runner. Steady, efficient, and capable of traveling a vast distance over time. Instead of combustions, electrical propulsion uses solar panels or nuclear reactor to generate energy. It's quieter and cleaner, it doesn't produce any harmful emissions, and it's remarkably fuel efficient. Because first, it has a high specific impulse, delivering more thrust per unit of propellant. Second is the low propellant requirement. It only uses a fraction of the propellant using chemical rockets, which reduce the payload requirement, allowing it to run for years. With the little thrust propulsions, it makes it suitable for really delicate missions. It's not about speed, it's about endurance. And how electrical propulsion does it, it's by accelerating, building then momentum over the time. But electrical propulsions are more complex than it seems. Let me break it down for you in a way it's easy to understand. Let me break it down with some visual and show you step by step. The system begins by introducing xenon, a noble gas, into a cylindrical chamber with an open end on one side and a closed end on the opposite side. Xenon is ideal because it's inert, easy to store, and its high atomic mass makes it easier to ionize and produce thrust. And the neutrally charged xenon only fills and distributes inside the chamber area. In the chamber, an electron gun device typically contains a material like tungsten, covered by barium oxide at the front, which is surrounded by a resistor. As the resistor is heated, the material inside warms up, and through a process called thermionic emission, it will start to emit electrons, similar to how vacuum diodes work. And a certain amount of xenon is introduced in the back of the tube. The high temperature environment allows the creation of plasma since the electrons collide with xenon atoms, which cause the atoms to lose an electron, creating positively charged xenon atoms. And now, as you can see, the same reaction that occurred in the electron gun now takes place on a larger scale. Now comes the magic. The chamber has two grids. The inner grid carries positive charge, while the outer grid is negatively charged. The electrons are naturally pulled towards the positive grid, but are repelled once they pass through due to the negative outer grid. On the other hand, Positively charged xenon ions initially face resistance from the inner grid positive charge, but as the pressure builds, they force their way through and are then accelerated by the pull of the negatively charged grid. These grids create a powerful electric field that accelerates xenon ions to incredible speed, far surpassing the exhaust velocity of traditional chemical rockets. But there's a problem. Without balance, the xenon ions would be drawn back to the spacecraft. To prevent this from happening, a second electron gun placed on the outside of the second grid fires electrons at xenon ions, returning back to a neutral charge. As a result, the xenon atoms can continue to exit the ion engine at a high velocity. This ensures the spacecraft to continue moving forward following the Newton's third law. Every action has an equal opposite reaction. Until now, one of the biggest challenges with electrical propulsions is the low amount of thrust they produce, which makes it unsuitable for traveling fast or landing on planets. Let me put it into perspective. An ion thruster like the one used in NASA's Deep Space One mission produced just 92 million newtons of thrust. That is roughly the force of one sheet of paper resting on your hand, compared to 7,607 kilonewtons of thrust generated by a single Falcon 9 rocket during launch. That's worlds apart. And that is because the mass of those little tiny particles is so small that it makes the overall force minimal. Another challenge is testing those electrical propulsions. Ion thrusters rely on empty space to run effectively, but with the charged ions in the atmosphere, this engine will be completely disrupted, effectively neutralizing the engine thrust. Additionally, atmospheric resistance is far too great for those little tiny atoms to achieve a meaningful acceleration. To truly understand their capabilities, we have to test it in space itself. One really promising solution would be clustered ion thrust. By grouping multiple thrusts together, we can significantly increase the amount of thrust produced, making them viable for larger spacecraft, but also for more ambitious missions. Meanwhile, clustering increases the heat load in the system, requiring then advanced thermal management solutions. Without proper heat dissipations, the lifetime and efficiency of the thrusters could be compromised. That leads me to the last and most exciting part of the video, where I will show you how I tackled three problems: the low thrust, thermal management, and the testing problem, by doing a simulation only on my laptop. Now let me walk you through and explain you the main points about how I simulated and tested the thermal behavior of a 2-thruster NPT-30 cluster, which by the way uses iron instead of xenon. In our case, we want to keep temperature within an operational range of -40 Celsius to +40, even with multiple thruster running. If you want more details about each line of code I wrote, go check out the article. The link is in the description. Before running any calculation, I had to set up the core structure of the simulation. Step 2 is modeling material properties. A key part of simulating heat transfer accurately is defining how materials behave under different temperatures. Instead of using fixed values, I wrote functions to define the properties. Now, heat doesn't just move around freely. There are key mechanisms that govern how heat is transferred between different components. For thermal contact resistance, when two solid surfaces are in contact, they don't transfer heat perfectly. This microscopic roughness and this resistance depend on pressure, material hardness, and thermal property. View factors is the key for modeling radiative heat transfer between surfaces, determining how much radiation emitted from one surface reaches another. So to keep things organized, I built a Python class called thermal simulation. This simulation is divided into a mesh of 50 elements, balancing accuracy and computational efficiency. More elements means higher precision, but also more time-consuming calculations. So the key components in this class is first the init function. Initialize thermal parameters, physical dimensions, mesh parameters, as I said, and heat transfer proportions, and also heat source. The second one is setup geometry function. So this creates a 3D grid of the simulation domain, setting up each axis and defining the regions for each element of the thruster. Apply contact resistance function models heat resistance between components and compute thermal resistance at components interface. So here you can see function we used at the beginning in thermal properties, which is contact resistance. This is the foundation of the thermal simulation. It runs the numerical solver to compute the temperature distribution between those two thrusters and the middle sheet. The data source, like the thruster power, is set up to 65, which was taken from the NPT30I2 1-unit datasheet. For the ambient temperature, it was set up to 4 Kelvin, which was taken from a research paper made by KTH Royal Institute of Technology School, which I was inspired by to do the simulation. I will put the link in the description. Now comes the part where physics meets programming. Let's go back and see the function that's given. The first one is get index. It converts 3D grid to coordinate into a 1D index for efficient memory storage. Second, to identify if a point is on the outer boundary, we use isSurface function. That returns true if the point lies on any of the domain boundary. Third is interface point. Point lies at an interface between two regions, such as the thruster and mill sheet. If a point is in region 1, has at least one neighbor in region 2, it is classified as an interface point where special heat transfer calculations like contact resistance, for example, must be applied. The last one is find neighbor index. It finds nearby grid points for heat exchange computation and returns the grid index of a valid neighbor if one exists. Good to compute heat transfer across different components. With everything set up, I implemented the iterative solver that updates temperature across the system until it's stabilized. How it works is, first, it starts with initial temperature guess, then iterates through every grid point, updating temperature based on neighboring points, accounts for emissivity, polished or anodized surfaces, and runs until convergence. Now keep in mind that the error scale of 1 multiplied by 10 to the power of -5 is totally arbitrary. Now the exciting part of our result. The visual function creates a 3D structure of the temperature distribution by extracting the temperature values from the solver and uses a scatter plot. Once the simulation is complete, the color represents different temperature zones, making it easy to see heat concentration areas. So the main function here just checks the result. So if it is converged, but here it's set to true, so it will be always converged, it will show the results. But now there's some problem. As you can see in the picture, in the results, all the grid points is set to the same color because they are all at the same temperature set to 284 Kelvin, which is not what we wanted. We can also see that in the heat energy balance, the total heat input and loss is not as we wanted compared to the propulsion we gave them at the beginning. So that is also something to solve. As for the material properties and at maximum temperature, it looks kind of good. We can see that the temperature is at 285, which is 22, and it is within the operational temperature range that we wanted. So it's acceptable. The thermal conductivity didn't really change, also with the density. In summary, some results were acceptable, but some adjustments are needed. For now, for the sake of time, I will move on to a new project, writing a review paper on performance difference between indium and iodine propellants. Thank you a lot for watching this video. If you'd like to stay updated on my projects, make sure to follow my Medium and LinkedIn. You can also subscribe to my monthly newsletters for updates and insights. See you next time.